Okay, that we do want to be super solid at. Honestly, once you understand how it works, it just takes practice. Like, just the more you balance, the better you'll get at it, and the faster you'll get to, which for AP is key, right? It's the speed at which we do things, okay? All right, open up your note packet. We are on page 4, and let's learn about these things called precipitation reactions. Now, with what we're learning today we are heavily focused for our chemistry triangle on the symbolic side. Okay, how do we write these precipitation reactions? As well as what is happening that we can't see. So we're going to draw some pictures of inside the beaker. On Friday, we're going to do a lab with precipitation reactions, so you'll get more exposure to this. I'll show you 2 demos today, but on Friday, you'll do like 46 different reactions.
Can we be the video people?
Yeah. If no one else wants to, yes. But yeah, so kind of keep that in mind. So first off, what it is, and then we'll break it down. So a precipitation reaction is a reaction that results in the formation of an insoluble product, which means it's not dissolved. Okay, keep in mind chemistry vocabulary words. Insoluble means it's not dissolved. Now I did this demo last time, but because some of you didn't get to see it in person, I'm going to do it again. Okay, so this reaction right here is a precipitation reaction. The insoluble product is signified by that S. S means it's solid, which means it's not dissolved, which means it's insoluble. Okay? In terms of what we see, what does AQ mean? Good, aqueous, aqueous, however you speak. What does that mean, though, when something is aqueous?
It's dissolved.
Good. So this right here is aqueous potassium iodide. So it is this. This is its symbol. This is what it looks like. It looks like water because it's been dissolved in water. Okay? Hopefully not. If you're drinking water that tastes like this, you might.
Probably tastes like bananas.
Okay, this one is aqueous lead nitrate.
Wait, what?
Okay, same thing. The lead nitrate is a solid, but I dissolved it in water. Okay. Pour them together. Everyone ready? Don't blink. 1, 2, 3.
She said that, I believe. Oh, yeah.
Oh.
I saw, yeah.
So for those of you that are here, if you weren't, you hopefully saw it on the video. But that's how you make orange juice in the morning, right? Yeah, orange juice is banana and what else did we say?
Yeah.
So the precipitant, once again, is we didn't make a yellow liquid, we made a yellow powder that's just stirred up. So I'll show you it from last week because it settled really well.
Is it yellow because of?
Here's the same thing as it's settled. So I'll bring it around and you can look at it from below. There's our yellow precipitant. So that yellow powder at the bottom is that lead iodine.
I thought it was yellow because
Banana's
of
yellow.
Yellow, exactly.
Weird
That is
coincidence.
true science.
But the potassium's not in the yellow, right?
What if there is not lead?
I think there's lead in bananas, yeah.
Like, I'm 90%
We
sure.
have concluded.
90% sure.
Don't eat banana peels, you'll get lead poisoning.
Okay, so our goal today, everyone, is to write out these precipitation reactions. So we're going to learn how to write them, predict what's being made, and then simplify it down to what is known as the net ionic equation.
Oh my gosh, they put
Okay.
people in that flash. They're drowning. Oh my gosh.
It's like it's a joke. Get it?
Oh, that took me a long time.
You're not,
Okay.
because the solution is the liquid. So
Yeah.
you're not part of the solution, and you're part of
Okay.
the. Moving on.
You're-
Okay, so solubility is this idea of whether things dissolve or not. The whole idea, once again, is all about positive and negative attractions. As the things are floating around, if the positive and negative are strong enough, they'll come together and stay together. Now, what's important to recognize is that doesn't always happen. We talked a lot about salt and drawn pictures of it, right? Where if you take salt, take your hands like this, pretend one hand is Na and one hand is Cl. Simple but important. What does salt do when you dissolve it in water? Show me with your hands. It breaks apart. Why? Yeah, the polarity, right? Remember, Mickey Mouse's grab onto it, pull it apart. Well, sometimes this link is stronger than what the water can overcome. And so it doesn't come apart and it stays as a solid. Those are our insoluble precipitants. This right here is a list of solubility rules that scientists have figured out. Hey, these things don't stay together, or they always stay together, or sometimes stay together. First off, you do not need to memorize this box, okay? Once upon a time, you actually did for the AP test, but luckily they've gotten better and realized memorizing is dumb. So we're not memorizing, okay? But we do need to understand how it works, and there is one part of it you do need to know. So underneath that table in your notes is this. Write a big capitalized note to yourself that I do need to memorize this note. It's pretty simple, but actually it's really, really helpful by just knowing this. What this tells us is all sodium, potassium, ammonium, and nitrate salts are always soluble. What that means is it doesn't matter what it's paired with. Anything with sodium, so just to give you some examples, the sodium chloride, sodium carbonate, sodium acetate. All of these would be soluble because they have sodium. So it doesn't matter what the sodium is with, it will always dissolve. Keep in mind, soluble means dissolve, break apart.
Bananas can resolve.
Okay.
I put a banana in some water for long enough.
I think it would, because bananas have potassium.
Yeah, there's potassium in it.
Eventually, well, but it also has lots of other things too.
Yeah, but if there's
Right, it has
any potassium in it, then it dissolves in water.
Okay, we'll just, yes, the bananas will dissolve. We'll just say that.
Yay!
Just kidding, that put me on film saying that. Okay, so let's try a problem. First step is we've got to figure out, okay, when something dissolves and breaks apart, what possibilities are there for new combinations on the other side, or in a sense, predicting the products? Okay, so step one, I'm going to write my reaction down lower. It tells us that we're going to mix some magnesium nitrate with some sodium hydroxide. Now, what's important to recognize here is that because these things are both aqueous and they're ionic, they separate. So the way I kind of think about a precipitation reaction is kind of like a dance, okay? Where magnesium is dancing with nitrate originally, and sodium is dancing with hydroxide originally, but once you pour them into water, they separate and maybe find a new dance partner. Now what's significant to note though is they pair up in a particular way. Magnesium will never dance with sodium. Anyone know why? Look up here on our table. Why would magnesium never dance with sodium? There we go. They're both positively charged. And two positive things, right, aren't going to come together. Good, have a smile for that. So the way the dance works is the first will always pair up with the last. And then these two will always at least have the possibility of pairing up, because positive, negative, positive, negative. Now, when they pair up on the other side of the equation, you have to rebalance their charges. And that's probably the hardest part of this, or takes the most time. So first step here is let's figure out what their charges are so we can balance them out on the other side. Yeah.
You're about in the circle.
Oh, the circle.
Like,
Oh,
no.
Wait,
Not
actually,
yet.
no.
Not
You're
yet,
fine.
you're almost.
If you
Just
drew,
So
like,
if I
already.
drew my answers over here,
Yeah, you're good.
good.
there's a weird glare from the projector. And if I write on it, people who watch the video can't see what I write. And I always forget about it, and I write like answers right in the middle of it. And- okay. We're gonna try this again. The last time it never worked. Where's the middle of my sunshine? Like right here?
That's a little over. No, the other way.
No.
Up a
Okay.
bit.
Okay, that's the
Perfect.
center of it. That's the
That's
center
the
of
center
it.
of the circle.
Now
That's
just
the
draw,
center?
just draw like a,
Look at 2-inch radius.
2-inch?
Probably more than that.
a three. Yes,
Perfect.
yes.
Oh, yes, that's
Oh.
Did you can't even
Perfect.
definitely not 2 inches.
Okay, now don't let me erase this. We do this every day. Okay, here we go, everyone. For a smiley face, don't say it out loud. Show me on your fingers, keep it underneath your chin. What charge does magnesium have in an ionic bond? You can look at the periodic table if you need to. We already identified as positive, but positive what? Show me with your fingers magnesium's charge. You're showing me this.
Let's
Oh,
go.
yeah.
I'd like second guess right
Can someone remind us how we found that?
You count.
1, 2,
2.
Good, so we're counting the columns, skipping the middle block, right? Okay, alright. Nitrate, now there's two ways you could find nitrate's charge. One is you could look at our polyatomic chart that I gave you a while back that we might want to pull out here in a second.
Oh.
You can also kind of go by backwards balancing, because magnesium has a +2, and there's 2 of the nitrates, so that means its charge must be -1. Does anyone, we found last period a lot of people were missing it, and I don't know, maybe I never gave it to you. Did I give you guys a print, like a polyatomic chart for you to keep?
You gave us the, not that it's done.
No.
You gave us like it as part of our homework assignment.
No, it doesn't.
I don't know where that is.
Oh, yeah, it's
so.
It's pink
Yeah,
for you.
Yes, it's part of a
I'll
homework.
take it.
Anyone need one? Or
Yeah,
maybe
I don't have that in my.
I'll spread some out and then you can have it to look at today.
Which you want?
Did you just pull it out? Oh, you have yours right there. Okay. Yes?
Wait, I
That's
wanna
why
know-
last period we were like searching through and I think you want another? Yes.
He wants it. He's gotta have both colors. You can't use the rare one.
Yeah.
Did you find yours, Isaac?
You can't risk losing the
Let's go.
Oh, I found it.
Freeze them in a
Give me yours then.
Yeah, I
You
do
don't
too.
need that.
Okay, can someone give one to Gavin if they found theirs?
Thank you, Taylor.
Oh, I guess this has it on the back. Anyone else want one? Okay, coming back up here. Okay, for another smiley face, show me on your fingers how many, what's the charge of sodium? This big stack right here. Students at home, this is the polyatomic chart. If you don't have one, email me, I'll send it. Okay, if you're showing me a 1, have a smiley face. And then hydroxide is -1. Okay? So now we gotta pair them up with their new dance partners and balance it out. So magnesium's gonna pair up with hydroxide. Magnesium is +2, hydroxide is -1. So it's gonna be MgOH2. So we need 2 hydroxides to balance out the 1 magnesium.
Does that mean there are gonna be extra sodiums?
No, but we might have to do some balancing.
No. Okay.
So I guess there's 2 types of balancing. Let's keep going with this, Taylor, but I think I see what you're asking. So then, sodium's gonna pair up with nitrate. Sodium is +1. Nitrate is -1, so they're a perfect match. You just need 1 of each. NO3. That step is balancing the charges. You then might have to balance the equation with the big numbers in front. Which in this case, I would need a 2 here and a 2 there.
Of course.
So you balance their charges, then balance the equation. Questions on pairing up the products? Now our next step is to determine of the products, are they aqueous or are they going to be a precipitant and be solid? So first off, based off the rule we're memorizing, which one is for sure aqueous?
Sodium.
Sodium, yep, so put a little AQ next to this one.
I'm just too smart.
Now this one's not in our memorized list, so go to your solubility rules with me, everybody. Right up above. Okay, find hydroxide, because they're listed by their negative anion. And we see the hydroxide is generally insoluble, except with an alkali metal, which means group 1, or ammonia. So, since it's not with either of those, it is insoluble, meaning a solid. Now, just a heads up, most of the time what I've seen from the AP test is they don't give you this chart, but they just say there's a precipitant that forms, and one of the options always has one of those memorized ones that you can say, okay, this is aqueous, so by default, the other one must be. If you're given the chart, then obviously you'll want to check them, but if not, most of the time it's just like, you can kind of process it elimination. So, questions so far? Okay, this right here is what we call the overall molecular equation. It shows you everything that's there, every possible combination. What we're going to translate this into is what is known as the complete equation.
No, circle.
No! Just see the
Every
outline.
time. My hand just...
Let's go.
You did it.
Circle, circle, circle.
Just
Telling you, I know
It's
it's
just
Sharpie.
Well,
I have chemicals that can get the Sharpie off at the end of the year. It's fine.
Well, the problem is that the circle moves every time because the iPad moves.
Oh, that's true though, huh?
You could just have a like a circle, like
just
a
screw it in
hyper. And you just line
Tape
it.
on
Like a little magnetic circle.
Yeah.
Dude, that would be really cool. Or what if you put a super small circle on the camera lens?
Yeah, I agree with
I
that.
don't like that. Okay, so
See, there's a song of Sam.
the complete equation, everybody, shows you what I think of as the true form of the reaction. Okay, the molecular shows you, here's what I'm mixing, here's what it's making. But this is showing us what it looks like at the molecular level. So we're gonna write it and draw a picture of it at the same time. Okay, so this box represents potassium nitrate, so this little flask right here. We could magic school bus into this beaker, right? Because it's aqueous and because it's ionic, the lead and the nitrate are separate from each other. So we're going to draw a Pb2 plus and 2 NO3 minuses. So if you want to draw an arrow just to help you, so this really looks like that. Right? Because they're separate from each other. Potassium iodide is also aqueous and ionic, so it will also separate. So we're going to have K plus and I minus.
You don't have to draw two of them,
We do why, Gavin?
and then two in front of it.
Because there's a 2 in front of it. And if we don't have the right ratio, right, then the reaction wouldn't happen. So, let's add another one.
Which says that on the
Now, don't say it out loud. Here's the smiley face question. Just nod your head. Would it be wrong, or would it still work if I did a third set? Nod your head yes or no. For those of you that are like, a little bit of everything. The answer is yes.
Yes!
Let's go!
I just saw Taylor doing it.
I was about to
You
take
go in the
my
back out of
Gavin.
advantage. It gets
Okay,
all over.
Taylor. Oh, because Kevin's in the back, so he can just take a survey. It's like the Who Wants to Be a Millionaire, like ask the audience. Right?
Yeah,
Yeah.
it works, so. Smiley says.
Me, you have a message.
Oh, you can just add it
Message?
to other
Yep.
message.
From who?
Message like that one. It's like.
Okay, Taylor, why? Why does that still work?
Because in the final one, there would just be a K potassium iodine, like
Yeah.
really
Okay, this is
be there.
fundamental and often a huge misconception. The balanced equation just tells you the ratio it needs to react. You can have extra stuff. That just means on this side you're going to have extra stuff floating around too.
Let's go, Taylor, we did it.
Okay? I kind of think of it as this is my recipe.
I actually got that.
Okay?
No, I get it.
This is my cupboard. You can have more ingredients in your cupboard than what the recipe calls for. You'll just have stuff that didn't get used. Does everyone see the difference?
Yeah.
So you need the minimum. Without the minimum, the reaction won't happen because you don't have enough stuff. But you can always have more. You'll just have leftovers. So, okay, very good. Now, coming to this side, okay, this box represents our final beaker once I've poured them together. Okay? What does this little S tell me? Solid, right? Those things are not separate. They're together, so we're going to draw it like this. As a clump on the bottom. And label it as PbI2. They aren't ions, they're a solid precipitant that forms. What does this mean about my potassium nitrate?
It's not solid.
So it's dissolved, and are they together or apart?
Apart.
They're apart.
They are like all of I know the end of
So we're going to have K plus and NO3 minus. Now, just to show you, if this is what I was to have originally, then our final beaker, I'm going to draw in green again, would also have a third K floating around and a random iodine that had no lead to
just
pair
that
up.
lonely eye.
That's so relatable. That's deep right there.
Okay? Now, we're going to write this in an equation form. Okay? So what we have happening here is we have Pb2 plus, we have 2 NO3 minuses, we have 2 K pluses, 2 I minuses. So this is what I mean by the true form. It shows you how they're behaving, how they exist, turning into 2 K pluses, 2 NO3 minuses, and PbI2 solid. That is known as the complete equation. Yeah, Zach?
Do we have to like put the aqueous thing on the other ones, or just because like you only have the one on solid?
Oh, good call. I'll be honest, things only exist as ions in aqueous solution. So by labeling it with its charge, it kind of like by default tells you it's aqueous. I've actually, like, you can put it there. I've never seen them dock points for not putting it there though. So for simplicity, you don't have to. Does that answer your question? Yeah, good question, or good comment though. Now, what I want you to notice here is there are two things in this reaction that aren't really doing anything. They're just floating around on both sides of the equation. Who are they?
Water.
Oh yes, water is there. We didn't draw it. But you are right.
I totally thought it was water.
There it is.
A and
2 K.
Good. So circle here that our K, notice is K here. It's exactly the same on both sides of the arrow. Same thing here.
So sad.
And if you look at our picture, that's all it's doing. It's floating around, floating around. Oh, look, they're still just floating around.
Dude, they're so lonely.
These are known as our spectator ions.
Oh,
Oh
Taylor, what have you done?
no. How the,
I'm too strong for the force.
oh, now the circle's gonna be in the wrong spot.
Wait, no, it's actually still in the right spot.
Should be, maybe. One of these days, I'm gonna get a real tripod. Okay, that's still pretty good.
No, 'cause it doesn't move as further.
Okay, sorry people at home. Got you a little dizzy there. Okay, so potassium and nitrate, everybody. These are classified as our spectator ions. In a sense, they're not really part of the reaction because they don't do anything to make something happen. So the end goal of today is to write what is known as the net ionic equation. I'm going to write it down here. This will go in your next box on your notes. The net ionic equation gets rid of those spectators and just keeps what's happening. So our net ionic equation would be Pb2 plus reacting with 2 I minuses to make PbI2 solid. And that is the end goal of our objective today, is to get to a net ionic equation. Now, we have 3 reactions here, 3 equations. We have the molecular equation, which is this one, the complete equation, and then the net. The complete equation, I guess you could say, is optional. If this helps you get to here, you can write it. But if you can go from here to here, I've never seen a question where they ask you to write out the complete. But if you need that visually, you're welcome to. General questions right now? Okay, let's try a practice problem. Oh, there's your blank right there for the next one. So what we're left with is the net ionic equation, which only includes what's turning into the precipitant. Okay, let's try this one. Oh, side note. Mine up here is different from what's on your paper. I don't know how that happened. So
Just ignore what's on our paper.
cross off what's on your paper, which says, the first part's right, barium chloride. Then cross off the second thing on your paper, potassium sulfate. Cross off that and write sodium carbonate. Tape. Failing us today.
Tape is so weak. Are we allowed to work on this with the table?
Yes, I'm actually going to do the first part with you too, but.
It's like warning.
Yes, yes, yes.
The AP test will not include this because you were not able to watch.
Okay, carrying onward. Okay, I'm going to do the first part with you to get us started, and then I'll have you complete it for some smiley faces. Okay, so step 1, I'm going to write some steps down if you are a process-oriented person. So to get to a net ionic, that's the end goal. Step 1 is you do have to write the molecular equation first if it's not given. Okay, the biggest thing with the molecular equation that you have to make sure is you make sure that you balance their charges. That's the biggest mistake I see made. So, barium is B8. Chloride is Cl. Barium has a charge of 2 plus. Chlorine has a charge of 1 minus. So when they balance, it should be BaCl2. It tells us barium chloride is going to react with sodium carbonate. Sodium is Na and it has a charge of plus 1. Carbonate has a charge of, that one's on your chart. You can't remember. Eventually we're going to memorize the polyatomics, but for now you can just look on your paper. Carbonate is 2 minus. So then when they balance, you need
2 sodium.
2 sodiums for every 1 carbonate. Now, do the dance. Switch partners. Barium's gonna pair up with
Carbon.
carbonate. You've got to rebalance their charges. But they're +2, -2, so that's convenient. So it's just BaCO3. Sodium pairs up with chlorine. So it's just NaCl. Questions on step 1?
Good.
That's normally the longest one, especially when it's in word form. You have to change it to symbolic form. Okay, step 2 is we need to balance the overall equation.
Don't you need 2 NaCls?
Well, it's just like the.
Oh, balance overall.
So you have to throw a 2 in front of it.
Thanks, Taylor. So that's what that means, is we gotta balance with the big numbers. Hey, everyone remind your table buddy really quick,
Okay.
just to make sure we understand. What's the difference between this and that? Go, remind your table buddy.
So that means that so on the first one there are like 2 things. On the second one, 1 thing, 2 different things.
I think Harley can be your table buddy today.
Yes.
Okay, I heard some good things and I saw some good hand sign language that I think was sitting next to too. If you said something along the lines of, this means that there's 2 separate NaCls, and this would mean that they're all connected as 1 molecule, then you can have smack each other.
Let's go.
It's like exactly what you said.
I pretty much just stole the answer from you.
No.
Okay, step 3
That would be like this attitude.
is we need to determine the precipitants. Or in a sense, we need to label AQ and solid. Now, for future reference, there are net ionic equations that instead of the precipitant being a solid, the precipitant could be actually a liquid or a gas. We're not gonna deal with any of those right now, but just so when it comes up, you don't like freak out too much. But all 3 of these labels all count as precipitants. Because liquids don't separate, gases don't separate, and that's the biggest idea, is it's not separating or it's not dissolving apart. Okay, going through our list here to label, so we know that these are both aqueous. Because the problem told me they were solutions. Also, it doesn't really work if the beginning things aren't aqueous. Okay? Coming on this side, I know one of those is for sure aqueous.
Oh, that's that second one.
There we go.
Sodium.
And so then this would be my precipitant.
Because it has sodium in it.
And sodium.
Okay?
Sodium.
Sodium doesn't believe in sticking together.
Step 4 is we need to remove the spectators.
Get out.
All the homies.
It's like all the football games nowadays.
Yeah,
Just
like
remove all the
COVID here, no
spectators.
spectators. Okay, how do I know who's a spectator?
If they don't do
They
anything.
don't.
Yeah, they don't
They're not
change,
a part
they
of
don't
the
do anything. Pretty much what I do is I focus on what did do something and then get rid of the rest. So in this case, I see this is my precipitant, so barium and carbonate are important, which means
Sodium and chlorine are not.
those are my spectators.
Frick sodium.
Get out.
Okay, so to write my net ionic equation, I need to turn them into ions and leave out the spectators. So I'm gonna have barium 2+ reacting with carbonate, turning into barium carbonate. And that's your final answer.
Wow,
Questions on getting from here to there?
that's beautiful.
Can they react and have there be two aqueous solutions?
Say that one more time, Taylor.
Can they react and just be like two aqueous and two
Ooh,
aqueous?
you tell me.
I mean, I'm
If this is
assuming
aqueous
yes.
and this is aqueous and that's aqueous and that's aqueous, what happens?
Nothing.
So next time in the
So
lab,
you wouldn't ever do that.
when you pour two things together and don't see anything, that's what's happened. Yep. No, great question. I must not use that. So,
Dang it, Taylor,
It
you're
would
so
work
smart.
this one.
okay, we're gonna have you try exercise 4.2b with your table buddy. Okay? Here's what I want you to do. Everyone pause for 1 second. Give me your eyes here. Give me your eyes. I know some of you are so excited to do this problem. Okay, you're gonna do this problem with your table buddy. Once you've completed it, you'll raise your hand. I'll come give you the thumbs up or the let's try that again.
No thumbs down. So let's try that again.
Yeah. Remember, no pessimism.
It's verbal, so everyone knows you're doing it.
Exactly.
Okay, once you have done this and passed it off, knowing like, okay, we're good, then I want you to get started on tonight's homework assignment in the packet, which is homework 4.2. Okay. All right, ready? Begin.
Do we have
So
to turn
fast.
4.3 on?
Not till like 4 hours. Oh, this class is-
Okay, wait. Calcium chloride.